Bismillahirrahmanirrahim. Welcome back to my channel. I'm back with a video. This is going to be a series on GnuRadio tutorial, and last video I think we have done it was on AM demodulation, and before that we did AM modulation using GnuRadio companion. Then we did AM demodulation in GnuRadio, and then we're going to do now FM modulation in GnuRadio. So what we're trying to do, what my goal is to actually look at your physical definition, physical equation of your systems, like for example AM, FM, and of course even like higher modulation scheme. By just looking at it, let's pick up those equations and convert them in a form of a flow graph into a working system. This is what my goal is throughout this series and what I want to achieve through this series. So in last video we did demodulation. Before that we looked at an AM modulation. We looked at the mathematical equation and we transformed them using the blocks which are available in GnuRadio companion. Exactly what we want to do in this video. So if you were to look at it, this is a general equation for your FM system. So let's just go through this, and we're going to transform this equation using GnuRadio companion, and we're going to see if this equation indeed turns out to be an FM system, an FM equation. So you have some cos signal which is AC cos, and then inside the bracket you have 2 pi FCT plus some beta function sine 2 pi FM of t. Alright, this is a generalized equation, and we're going to break this down into different components. So FC, as we know, this is going to be your carrier frequency. FM is going to be your modulating frequency, and then you have some term which we are calling it beta. Beta is similar to, it's called modulation index. Beta is what? It's a modulation index. It's just some multiplying factor. Just like in AM we had modulation index, we were multiplying it by some factor 1 in AM, but this beta can vary from 0 all the way up to whatever number that you want to have. Let's say 10, 11, 12, 13. This is due to Bessel function. That's all you need to remember. We're just going to simplify this. So you have cos, you have some signal in carrier signal, you have a modulating signal. Your modulating signal is being multiplied by some function, some multiplied value, which is going to be beta. Now if you were to look at this, so what is the second step this equation is saying? This is actually, everything is done on a real signal, which is your cos signal. As you can clearly see, this is your cos signal. So that's why we removed this cos and we brought in our RE for real signal. And then AC is just e to the j 2 pi FCT plus beta sine 2 pi FM of t. That's all we have done. We have removed cosine because cosine is a real signal. Instead of that, we have just simply written real signal here, and then we have AC e to the j 2 pi FCT, the inside bracket term, along with the kernel here. Now the next thing is, if I know the bases are same, I can split them. The only way these two components are being added when the base is same, so I can just split them and multiply the bases together. So this is, if you have the same base, you can add them up, which is the top equation, but you can split them up like this. That's all you need to remember. Now if you were to look at this equation now, there are two components. Alright, there is this component, and there is some multiplying value which is related to your carrier frequency, which is FCT, and then this component deals with your FMT. So having that in your mind, and then this, they are calling all of this to S of t, which is some phasor domain. Okay, this whole thing. Now let's go to our GnuRadio and then just do the function as the equation describing it. As the equation describes it, let's perform exactly the same thing. The first thing I want to do is this. I want to take my modulating signal, which is in a form of a sine wave. I'm going to multiply it by some value called beta. This beta is nothing but a value which can vary from 0 to 10. This is just some modulation index. If you can see the table, like a Bessel function table, it's just going to be some multiplied value that is being multiplied together with some sign. Now if you were to look at my graph now, let's look at it now. So I have my signal source. Check this out. Alright, let's just follow exactly what the diagram is saying. Okay, look at this. now everything has changed because this was a cos term, so it has to be in real number, isn't it? Everything is in real number. Cos, because cos is being multiplied with this term and this term, so this is some real number. So that's why if you were to look at in your flow graph, you have chosen a signal source. I've just taken some random frequency, which is, I'm calling it M, that has an amplitude 1, which is a modulating frequency. And check out the color itself. The color itself represents in a form of a real function. Now this function, if you were to look at this value, just inside term, we're just solving for this. We're just mapping this in a GnuRadio flow graph. This is being multiplied by some beta value. Alright, so let's look at our beta value. Our beta value is given by multiply constant, which I'm calling it beta. Alright, all of those individual terms that you are seeing, like FM and the beta value and things like that, like this, you can use a range block like these, like range block for your beta function, range block for your FM function, and you can give the value and you can call them in the respective block. Alright, so beta function is being called here, where I've set a value of from 0 to 10. Alright, and then for your FM, I have chosen a value from 0 to 10 kilo, and then 5 kilo is your default value. That's why you have a default value of 5K here. Alright, nothing else. I haven't done anything fancy. All have I done is just map this real, the function beta times sine pi of t. Now let's just look at okay, every time you're not connecting a hardware device, alright, to your GnuRadio flow graph, you have to put a throttle block. That's all you need to remember. Alright, that's all you need to remember. If you're not connecting a USRP or any type of a SDR device, you need to actually connect a throttle block. That's all you need to know. Now here's the thing. Now if you were to look at this value, alright, so now that you have gone here, if you were to look at this value, when you want to convert, now the next thing that you want to do is this. I want to take this real signal, which is a real signal, and I want to convert it into a complex form, because if you were to look at it, look at this value. What is this value? I want to convert this signal into e to the j x value, isn't it? Doesn't that look like this? This is a complex signal. This is a complex signal because sine is a complex part of a signal, while cos is in phase, sine is quadrature. So you want to convert this real signal into a complex signal. In order for me to do that, we have something called a phase mod block. All right, phase mod block. So what it will do, whatever the signal that is coming in, which was a real signal, look at the output. It's just going to take that signal and it's going to convert that into a complex form. That's all it's going to do. I hope you're getting it. Phase mod, what it does, it will take your signal, input signal, which is in a form of a real signal, it will convert that into a complex signal. Alright, into a complex signal, because this is what my requirement is, because this thing is a complex function. Alright, this thing is a complex function. Now, the next thing I need to do is this. Now, the output of this is a complex function, which means that I need to, in the next, if you were to look at the next definition, after you convert your modulating signal, which is this guy, into a complex function, I need to multiply it by a carrier frequency, isn't it? This is 2 pi FCT, which is also going to be a complex frequency. All right. One thing that you need to remember, this phase mod output block, it cannot change. You cannot just change the color code of this. Input is real number, the output is complex, which means I have to multiply it by a complex signal, complex carrier signal. That's why I've chosen this to be 500K. If you want to look at the values, okay, so this is FC. So this FC is being called here again, where you have a default value of 25K, and then you go from all the way from 0 to 100K. All right, the 500K is your sample rate. All right, so far so good. So now if you were to look at it, what I'm doing, I'm actually taking this complex signal, I'm multiplying this by a complex signal, which is given by e to the j 2 pi FCT. Now if you were to look at it, your signal itself, your carrier frequency, is actually by a cosine signal. So I'm multiplying it by a cosine signal. So you have an in phase and quadrature. Quadrature is coming through here, and I'm just simply multiplying this with a multiplier block here. I'm multiplying it by a multiplier block here. That's it. Now the next thing I want to do is this. When I multiply this, the output is coming out. Now I want to look at this signal. I need to change this from complex to real signal. So in order for me to change this format from complex to real, I'm using a block, just a block called complex to real block. And this complex to real block is giving me some real values, and I'm observing that in both on my time domain and frequency domain block, as you can clearly see. That's all I'm doing. So if you were to look at the flow graph complete, so you have your signal source that is going out, is being multiplied by some beta value, which we are calling it a modulation index. Phase mod is converting that real value into complex value. This complex value is being multiplied by your carrier signal, which is being multiplied together and converting back into real signal. This is that entire equation which is being described here in this equation, if you were to just simply look at this. So this, everything is being converted in a form of a flow graph that looks like this. Now let's run this flow graph and let's see if everything is working fine. If you were to just hit play, and let's see. Beautiful. Now you can clearly see. Alright, I'm seeing a change in frequency. So this is just your modulating signal, which is your actually your what do you call it, a modulating signal. So let's just change this beta a little bit. Let's see. Now you can clearly see. Let me stop this. Now you can clearly see there's a change in frequency here. Then you have some lower frequency, then you have a change in frequency, which is much faster, and then you have a lower frequency, and so on, so on. So FM is taking place. I have a modulation index that is being set to 2.5. All right. I have a carrier frequency, which is FC, and then FM. I can just simply change this frequency component as I like. Now, the interesting part that I want to look at. Let's look at this. I think I have also explained when I did a demo of this using a oscilloscope and your function generator that this beta value is governed by some Bessel function, and that tells me how many sidebands will be produced. Set of sideband you will see. Now, if you were to look at it, so 0.5. All right. So let's just quickly look at this. Now, this is going to be a major frequency component, all right, which is going to be at 25 kilohertz. Now, the next component is going to be 25 plus your carrier for your modulating signal, 25 plus 5, which is going to be 30. So this is going to be a 30, and then 30 plus 25 plus 2 times FM, so that would be 35, and 40, and 45, and so on. So these are the number of sideband that you will see when you have a modulation index, I believe, of 0.5. So you have to look at your Bessel function, and then you will see that indeed if it's happening or not. Now, if you were to zoom out from here, let me just rerun this flow graph. If you were to zoom out from here, and let's look at this graph again. So 0.4. Let's go to 0.5 again. Right, let's go to 0.5. Now, if you were to look at this, so when you will generate this graph, we don't care about what's going on at negative frequency, all right? So this we don't care. We only care about this part where you have a carrier signal, which is right here. Then you have FC plus FM, FC plus 2 FM, 3 FM, 5 and 4 FM, and so on. And this is FC, then this is FC minus FM, which is 25 minus 5 is going to be 20, 2 minus 2 FM minus 3 FM, and so on. you get these negative frequency component because of Euler's identity, because when we're converting these complex signals and things like that. Otherwise, in real life system, when you're checking it, just like we also did an example using our digital oscilloscope, that you don't get to see none of this. So these are just redundant values that you see due to negative frequency concept using complex numbers. But this is what you should be observing from the. This is what you should be seeing. So you have FC plus FM plus 2FM plus 3FM and so on. FC minus FM minus 2FM, 3FM and so on. So this is how you actually take your equation and convert them in a form of a in a working communication system like FM and things like that. I hope you like the small tutorial on this. If you have any questions, just leave it in the comment section. Don't forget to like and subscribe to my channel.